Today, the speaker is Maciek Wielgus from Harvard University from Black Hole Initiative, who is also working on the Event Horizon Telescope project. And he will be telling us about the new results from the EHT. Thank you very much.
Thanks, Deborah. So hello, everyone. It's a great pleasure to talk to you about these new results. So this is something that we published last month. This is about the polarization of the M87 image. And, you know, I will start slowly with some intro and some recollection of the previous results. So let me start with the introduction of the Event Horizon Telescope. This is quite a big collaboration for the standards of astronomy. There are over 200 people participating in that collaboration from 18 countries, from over 60 institutes. And that's a photo of about half of the people involved at our meeting in Nijmegen in 2018, back in the days where we actually could meet together and have a photo like that. This seems to be totally impossible in these days. So that was the team of scientists. Now the object, our superstar, although it's not a star at all, it's a black hole. M87. M87 is a huge galaxy in a Virgo cluster. And this is actually the first jet that we have seen. Like about 100 years ago, we already seen in optical wavelengths that there is some feature emerging from the core of this galaxy. So back then we didn't understand what is that, what does it mean. So it was mostly seen, it is seen in optical, but it's mostly prominent in the radio. So throughout the years, we were building larger and larger telescopes, going to shorter and shorter wavelengths to beat the diffraction limit and to look into the core of this object. And by the time of 1960s, we already knew that there is some origin of this jet, of this prolongated feature, and that there is a radio point source from which it originates. But of course, in 1960s, we weren't able to resolve that source. So we were moving closer and closer and closer, and only in 2019, we actually imaged the resolved feature corresponding to this place where the jet originates. And that's what we have seen, this bright donut, asymmetric donut of diameter of about 40 microarc second, which became, I think most of the people have seen that image. These are the EHT results from 2019. So that was a bit about the source, about the team. Now I will talk a little bit about the shadows of black holes. What do we mean by that? What is the story behind imaging the shadow of a black hole? I will start in 1970s, although the story is longer and dates back actually to the work of Hilbert about the time that general relativity was first published. But in 1973, Bardeen calculated the outline of the shadow of a black hole, meaning the feature, if you had a wall of photons hitting the black hole from behind it, going to the observer in your direction, this is the outline of which photons would fall into the black hole and which would not. So this contour is referred to as a shadow of a black hole, or more precisely, we would call this feature, the edge of it, we would call a critical curve typically. And it is depending on spin. So perhaps it could be a way to probe the spin of a black hole. So this was a purely analytic calculation. Now, next step on the imaging of black holes is also synthetic. 1978, Jean-Pierre Luminet generated this pretty image. So now the difference is that now the source of the photons is not a wall of photons. This is a thin disk, a solution of Novikov-Thorne, and how the trajectories of photons would be curved. So what Luminet did, is he took, I think, 10,000 photons emerging from initial conditions from the Novikov-Thorne disk solution. He calculated numerically their trajectories, so how would they hit the screen of a distant observer, and then manually put these points on this picture. So this is a piece of art as much as a piece of science. Matplotlib didn't exist back then. People were doing what they had to do. So then another step 20 years later, this is actually the first consideration about a solution of an accretion that we really believe that is located in M87. It is not a thin disk. It's more like radiatively inefficient accretion disk, RIAF, radiatively inefficient accretion flow. So it's a thick, geometrically and optically thin donut around the black hole. And then the image would look something like that. And there was this claim made by Heino Falke, who is one of the people involved in the EHT project. Of course, back then this project didn't yet start. That the claim was that we could expect to image such feature within next few years. Heino is a theoretician, so of course he could easily say that, yeah, it's just next few years, and actually it took 20 years of technical developments in order to be able to capture this feature with necessary sensitivity and necessary resolution. Right, so when the Interstellar movie came in 2014, which kind of installed this idea of a shadow of a black hole in minds of people and in popular culture, and this is probably responsible for the big popular culture response to the image that Event Horizon Telescope produced. So where we are right now in terms of simulating such images, right now we can run sophisticated simulations, general relativistic magnetohydrodynamic simulations, where we can put a lot of different aspects of physics, including magnetic fields, including some bits of plasma physics, including GR. We can self-consistently trace the evolution of such systems, so we can generate not only pretty pictures, but also pretty movies of how we expect this feature should look like. So what to do in order to actually capture a feature like that? We are limited by the diffraction limit. Diffraction limit is lambda over d. So lambda is the wavelength, d is the diameter of your telescope, which you use for the observations. We know that this object is about 50 microarc seconds across. So let's say that we need a resolution of 20 microarc seconds to actually see something within that image, not to just have a blob. So if you do this calculation, and if you put 1 millimeter, which is pretty much for many technical and Earth atmosphere related reasons is as short as you can go with the radio wavelengths, when it turns out that it is required to have a telescope of 10,000 kilometer diameter, which is pretty much the size of the Earth. So we need a telescope of the size of the Earth. It is difficult to turn the Earth into a dish, right? I mean, we would need a lot of permits, construction permits, to actually turn every surface on Earth into a telescope dish, and many people could be upset about that. So we need to do the next best thing. And the next best thing is called very long baseline interferometry. So instead of turning the whole Earth into a dish, we consider Earth to be a dish, but one that is almost entirely empty. It's only capturing photons at a couple of locations where we actually have telescopes. They need to observe simultaneously. They need to track time very carefully. They need to look, of course, at the same part of the sky. And then by comparing two wavefronts incoming at two different telescopes, we turn this pair of telescopes into interferometer, and we can measure through the correlation measurement, we can measure the distribution of the intensity in a plane of the sky. And of course, the more pairs of telescope we have, the better measurements we can make. So we need, well, a lot of pairs of telescopes, and each pair would constitute such an interferometer. So this is the array that we were able to put together. This is the EHT as it operated in 2018. In 2017, which is the year of observations that I'm going to talk about, we didn't have GLT, and also SPT is not able to observe M87. M87 is a northern source. So really we had this inner part of the array available in 2017. So this is not much. This is really 1, 2, 3, 4, 5 different locations around the Earth, which gives you 10 pairs of telescopes. So 10 measurements doesn't sound like much to regenerate the image. Fortunately, we have a trick to play, and it's kind of embarrassing to call it a trick, to call the trick the fact that the Earth is rotating, but we are utilizing this fact. So as the Earth is rotating, the geometry between our pair of telescopes and a distant source is changing, which means that we sample different locations. So what we are actually sampling through interferometry are the complex components in a Fourier plane of the image. And they are related to the brightness distribution in the sky through something that is called Bann-Sitter-Zernig theorem. So what we are really sampling are the Fourier coefficients on a plane, and then we just need to reverse this Fourier transform to obtain the image. The problem is that the measurements are sparse, so of course we have to make intelligent choices about what to do about all these places in a plane that we are not sampling. But turns out it is not well, a very well constrained problem, but there are constraints to put on the image, such as positivity of the distribution of brightness that actually give us much more information and are able to regularize this problem. So this problem sounds difficult. It is difficult, but it's not tragic. We can perform imaging. Because I've been involved in data calibration a lot, I do really like showing this story of the data. So what happens to the data, we do need to physically load petabytes of raw signal recorded at each telescope. We need to put them on the planes and put them in the same location to perform the correlation, to compare these two recorded wavefronts. We do that in Haystack, Massachusetts, and in Bonn, Germany. Then there are subsequent steps of calibration to remove the spurious effect of the turbulent atmosphere, and only then we really get those Fourier components that then we can use to reconstruct the image. So this is really something that took us like 2 years to get from this left side of this to the right side of this slide. Okay. So why are we interested in all of that? What is going on when a black hole is illuminated by photons? So here we are shooting a bunch of photons in this animation from different initial conditions around the black hole. You see, this is the outline of the event horizon, what you have seen there. And now we are propagating them to the distant observer. You can see that the trajectories are curved, they are not straight lines, and you can see there is this lensing effect. So the outline that you see is actually about 2.5 times larger than the diameter of a black hole as it would appear in the flat space-time, meaning that there is an information about the curvature encoded in that image, so you can in principle use it for fun things like testing the general relativity or testing your favorite gravity theories. Okay, and that was the intro. How did I do? Like I took like over 15 minutes just for the intro. So that was the state of what we had in 2019, the total intensity image of the M87. So what we did add last month to it is this: we added information about the linear polarization. So I will try now to walk you through what is it that we've done and what is this hairy profile really, what does it mean? Well, quick spoiler, this is the orientation of the polarization vector. So this is something we would call EVPA, electric vector position angle. So it would be tangent to these lines at every point. This is what linear polarization of this source would look like. Okay, but to give you more detail, let's start with a very simple image. I'm sure you guys all know what polarization is, but it's like a good place to start to give something extremely basic. So if we have unpolarized light, the planes in which electric field and magnetic field vectors are oscillating, they are not constrained. It's pretty random. Then you can put it through something that would polarize the light, meaning it would only allow oscillations in particular plane to go through. So here you can see this is some vertical structure. So only the oscillations in a vertical direction are able to pass. So that's how you would get linear polarization. And in some sort of a simplification, we can say that what EHT did in 2019 results is we didn't care about the state of the radiation. We just put total energy image. So whatever is the total intensity, is there a polarized fraction, is it totally random? We didn't care at all. We just put the total energy pattern. So now we actually care about where is linear polarization. But it's not like we are generating ourselves with linear polarization. We're not using any sort of polarizer like here. It turns out that there is an intrinsic polarization in that source that I will talk about. This is related to the mechanism of how this radiation is generated, and synchrotron radiation is naturally polarized. So there is an intrinsic linear polarization in the source that with more careful data analysis we were able to recover. This is just a trip down the memory lane. This is the image from 2018 where for the first time we saw the total intensity pattern. So we see a bunch of happy people with the first image that was a year before publishing these results. But that was the first time that we really found a consensus about what are the data showing in terms of total intensity. So there's a parallel image from Max Planck Institute in Bonn with the first consensus images of linear polarization. So you can see some lines here. These are the linearly polarized patterns of this source. So that's the first time that we found out that we agree about the structure, we understand the structure, but also notice that this is July of 2019 and it was published in April 2021. So it's like 1.5 years between getting to this agreement and actually publishing things. COVID didn't help, but also it's really difficult to make sure that everything works fine. VLBI polarimetry is kind of, let's say, VLBI is very difficult, but polarimetric VLBI is order of magnitude more difficult, actually. So that was challenging. And I will talk a little bit about this data analysis, but just a little bit. I'll try to get to the interesting part of theoretical interpretation as well. So we published 2 papers. One paper is mostly about this calibration, analysis, and imaging. The other one is about the theoretical interpretation. It's, of course, the work of these 200 people, observers, data people, and so on. However, it makes sense to point out a couple of people for both papers that were mostly involved in this work, in writing that down. I am here. I was involved in this paper 7 very intensively. This is what is nice to see here is that it's such a diverse crowd in a sense that we have brilliant PhD students like Sarah Izaun, and we have people like John Wardle who are working on polarimetric VLBI and radio interferometric polarizations for like 50 years now. So we have a whole spectrum of different experience that people have in this team. Okay, so these are the people. Now let's go back to our stations. So it turns out, if you recall, that we are doing interferometry. Interferometry happens between 2 stations. It's not a single station measurement. it's like a double slit experiment, sort of. You do need two slits to do a double slit experiment. So it turns out that if you would just record total energy, then you could do this total intensity imaging through calculating correlations between intensities at two telescopes. But it turns out that if you record two orthogonal states of polarization at each of the telescopes, then you can calculate 4 different correlation products, right? Because it's 2 different inputs at one telescope, 2 different than the other, and you can calculate 4 different pairs what you correlate with what. And then it turns out by the algebra that I'm not showing, I prefer to show these pretty images of telescopes when I talk about this algebra, but then through algebra, you can, it turns out that from those 4 correlation components that are called coherency matrix, you can recalculate full Stokes representation of polarization, meaning you get the full information about total intensity, 2 components of linear polarization, and information about circular polarization. Just by recording 2 orthogonal components of the field at each telescope. Actually, JCMT had only 1 polarization, so JCMT didn't participate in this polarimetric endeavor. JCMT was only able to contribute to the total intensity. So we still have 5 different locations around the Earth for this polarization. So it is a bit of a loss, but not a huge loss. Okay, so just to tell you very broadly about what are some of the problems and what is interesting about this polarization. So this is ALMA. ALMA is looking at M87. M87 is not to scale. It's not that big on the sky. It's actually quite tiny on the sky. And during the night, you can see that, of course, the stars are rotating around or Earth is rotating, really. The rotation is around this apparent rotation of the sky is around the northern star, which is below the horizon, of course, because ALMA is in a southern hemisphere. But you can see that the image is rotating as this yellow square, so it's rotating with the sky, but the receivers are those green guys, they are tied to the Earth. So there is a rotation between the frame of the image and the rotation between that and which linear components of polarizations the telescopes are probing. This is blessing and a curse. It is bad because we have to do more bookkeeping to keep all those systems of coordinates aligned. But on the other hand, we get to probe different parts of the linear polarization. We get to probe different orientations. So then using that, we actually can detach the intrinsic properties of the source from the instrumental properties. So there are corruptions that are related to the instrument that are bleeding into all of this analysis. And because of this, we actually, it's easier for us to disentangle the two. So what you see to the right is the image that you would see if you had a linear polarizer and you would be turning this linear polarizer in different directions. So this is what you would see. So what is the component of linear polarization in particular direction? And we get to probe different directions because of this mismatch between the receivers and the Earth rotation. So even before we attempt to do the imaging to see the image, we can look at the data, and we can already see something. We can see that it's rather weakly polarized source because these guys are bluish more than reddish, which is good for the algorithm. And we know that the source is compact from the total intensity imaging. Another fun thing to notice is that there are actually differences between these days. So we already, from this point, we expect that we would see some difference, some evolution of the polarized structure between the days. Now I will talk about a little bit, well, a couple of tests that we can do to ensure that it's very complicated problem that we have a good handle of it. So this is just one test that we can do. This test is about looking at multiple different sources, not only about M87. We did observe multiple sources and we didn't publish on too many of them. We will at some point. So this is a comparison between components of the linear polarization seen by VLBI, so by the EHT, and seen by ALMA. So ALMA is an incredible array. ALMA is consists of like 66 top-notch, high-quality telescopes that were made to work together, so they don't have this EHT problem that every telescope is speaking a literally different language and we have to somehow patch them up, somehow make them talk to one another. But ALMA is very homogeneous. Of course, ALMA cannot see such fine details as VLBI because ALMA is like at most 300 meters across and VLBI is 10,000 kilometers across. Nevertheless, we can look at unresolved polarization, so like the total polarization of the source, and we can compare. QA2 is the ALMA provided value, which is, we are very certain about that. ALMA is well calibrated. And the thing on the horizontal axis is the value from VLBI for the total unresolved polarization. So if the two are aligning together, it means that VLBI is seeing the same thing as this well-calibrated ALMA array. So we want them to align on the identity line. And you see two components of the linear polarization, Q and U, both align pretty well on this line. So this is a confidence boost for us that okay, we seems like at least from that point of view, we know what we're doing. So when we know when we believe that we know what we're doing, we can start attempting to reconstruct images. So what you see here are the images that we first got back then in 2019 in Bonn during a workshop. These are the total 3 different pipelines. So 3 different algorithms that make different assumptions about the data, and we wanted to see if they all agree. So this is total intensity, and you see there is a decent agreement between different algorithms. Then the linear polarization. So what is the orientation of the EVPA, of the electric vector position angle, and where does the linear polarization live? They are also in decent agreement. So you see that they always find that polarization lives in the bottom right part of the image. And they also always show this pattern that it's kind of along the ring, but not exactly. But the orientation of those dashes is consistent between the algorithms. And this is another nightmare of calibration components of so-called leakage corruption. So leakage is an instrumental effect of, well, imperfectness of our receivers, meaning if you have a receiver that is supposed to only pick up the horizontally polarized light, of course, it's not perfect. It will feel a little bit of the signal from the orthogonal polarization, and we call it leakage. It's like the vertical component is leaking into the measurement of the horizontal one. And it's described with a bunch of complex numbers. So I will not go into detail, although this is about a year of work of a big team to figure out those leakage coefficients. But you can see that by comparing these patterns for different algorithms, that we got that pretty consistently, right? That the green dot is always here, and the blue and the red square is always about here. So another confidence boost that it looks like we understand this leakage corruption. We understand how our receivers are being corrupted by this leakage effect. Right, so now if we are confident that we kind of see the same thing, let's do it more systematically. Let's consider if our algorithm would be able to recover known polarimetric structure of the source. So we were testing our algorithm with multiple different synthetic data sets coming from those general relativistic magnetohydrodynamic simulations, but also with a bunch of geometric models. So let's just see for one of those models, from the one from the bottom right, how our algorithms are dealing with something of known structure. So this is the structure, and these are the synthetic observations of the synthetic EHT observations, and 5 different algorithms for the reconstruction. Now we added 2 more algorithms for some reason. Well, the reason is we want to be sure about what we see. And you can see how the 5 different algorithms are dealing with it. So it's not that they are all perfect. You can see, for instance, this guy wants to produce large polarization somewhere and there is nothing like that in the data, in the synthetic data. But on the average, they make different assumptions. And on the average, they do show this very similar pattern and a similar fractional polarization, right? Meaning the colors are on average pretty much the same. So the argument is that, okay, we have 5 different tools that produce different results, but they are pretty consistent. So let's average them down for the real data. And so then they will only show the parts that they agree about, right? So then let's go with the averaged images as our resulting images to even more be more confident about the structure. So this is how those 5 different algorithms, these are names of those 5 different algorithms, were able to deal with the real data from April 11th, 2017. And again, you see that there are slight differences. Some algorithms can give you more polarization than other ones. So probably this is artificial, but the average structure is pretty much the same. So if we average all of those down together, we expect that this is that would be the most reliable representation of the real source. Things to notice, well, the location of the polarized emission is pretty much the same. It's always weak. It's about like 15% is this greenish color. They are all pretty much this greenish color in this part. So it's rather weakly polarized, about 15% in this maximum region. So now we have multiple days of observation. So we can again perform this averaging between 5 methods and look at what it gives us for the 5 different days. And well, there are two ways that we figured out how to represent the results. The first one, good for scientists, and the second one, good for the public. So for all the public announcements, we actually went with the bottom row of the images, which contained exactly the same information as the upper row. However, I think they are much more pretty. It really looks like this kind of hairy structure winding around the black hole. I think they are quite pretty. But again, they have the same information content as the upper one. So if you prefer kind of maybe more scientifically looking plot, you can look at the top row, not the bottom. Now, this is another slide about the leakage calibration. I will try to be quick about it. This is boring calibration, but I talk about it a lot because it really took a lot of time. So I have shown you that there is some bit of agreement in how this leakage works, but the agreement is limited, meaning these are really distributions that we are getting. We were just showing some sort of best fitting values, but the distributions look more spread. So the question is, can our leakage uncertainty, that can be quite large, maybe it's this green point, maybe it's that green point, can this uncertainty in leakage influence the morphology of the image? This is a reasonable question to ask. So to answer it, we ran those scripts, we ran those algorithms with thousands of different realizations of the D-terms drawn from these posterior distributions that you see here. So we test all of those different combinations of D-terms to try to understand if it matters for the morphology of the image. So this is a picture to illustrate those efforts. And this is a lot to talk about, so I will try to explain what's going on. So this is the image of a ring, but resolved, meaning we just go around the ring. This is the position angle, so 180 degrees corresponds to the bottom of the image, 360 degrees corresponds to the top of the image, and we're just looking at the lines in these directions, radial lines in these directions. And we're looking at total polarization that we see in that direction, right? So the spread of those bands, the spread of those lines is how much leakage can influence the results. And you see that, well, it does influence the result a little bit. Maybe it's 20 microjansky per microarc second, not 25 microjansky per microarc second, but it's not the dominant effect. In particular, where is the maximum of polarization? It doesn't depend on the thickness of this band. It's always around here on April 5th, and then it moves about 50 degrees for April 11th. So, and it's not influenced by leakage that much. So this is what yet another confidence boost that the leakage corruption is not really changing things that much. There is a quantitative effect. There is no qualitative effect from the leakage uncertainties. Okay, so how can we extract particular information from those images of the polarized M87 flux? I will just give you a couple of examples of the quantities that we calculate to compare with our models. So first will be this net polarization. So this is this unresolved polarization that ALMA can see and EHT can see as well. But EHT on the top of that can see resolved polarization. So for the resolved polarization, we just go pixel by pixel and we calculate the average module of the polarization. So this will be necessarily larger than the net polarization, because things do not cancel out when you average the modulus, the absolute value. So you see that is net unresolved polarization is just about like 2%, maybe maximum of this distribution, and then this mean resolved polarization is about like 7% maybe. So it's slightly more. And when there are more parameters, I will just talk about one geometric parameters that the equation is like that, but it's easier to understand what this beta 2 parameter is doing with the illustration. That's the illustration. This beta 2 is telling you if the orientation of polarimetric polarization vector is more radial like that, more azimuthal like that, or maybe it's something twisty. So this is also useful parameterization of the morphology of the image. And now we can take different days of observations. We can take our 5 different algorithms for the reconstruction of the image. We can perform measurements of those quantities that I have mentioned, and we can put limits on what we expect from the real system based on these measurements. So you see, we are kind of generous in those bands. We really try that most of the methods or all the methods are within that band. So this is why these constraints are not extremely strong. They are like between 1 and 3.5% or things like that. But you see that there is really good confidence about that. There is also 2 independent bands in which we perform measurements. So they are shown as these dimmer and brighter points in here. So we have 2 bands, different days, different algorithms. We have a lot of redundance in all of those measurements that we make. So this got me to the theory paper. This will be shorter, but probably the most interesting part. I will try to do it in like 10 minutes. Hopefully won't take too much time. So this is again the team of the people contributing a lot to this theoretical part of the work. So let's start about maybe some justification of why we think it's so interesting to look at this polarization. Well, the polarization is tracing the magnetic field. which I will elaborate on later. And we are very interested in the magnetic fields around the black hole because we expect that they are driving with powerful outflows like jets. So we expect that magnetic field is absolutely very important. The twisted magnetic field is absolutely important, necessary to have those jet outflows. So they are energized and collimated by this twisted magnetic field around the black hole. That is our understanding, and something that we want to see proof of in the observations. This is another image or animation from the GRMHD simulation, where you actually see what's going on, that what is this symbiosis between the twisted magnetic field and the jet. So this jet, this outflow is really being collimated and being driven by this magnetic field. It also is most likely energized by the magnetic field, either through Blandford-Znajek process, where this energy is extracted from the rotation of the black hole, or Blandford-Payne process, where when this energy is extracted from the energy of rotational energy of the accretion disk. So whichever mechanism is right, Roger Blandford is a happy man because he will be right regardless. So now about synchrotron emission, a few words. Synchrotron emission is a very special kind of emission. So this is the emission produced by a charged particle accelerating in the magnetic field. So in our case, it's mostly electrons contributing, electrons looping, gyrating around the magnetic field line. So this is magnetic field line, and there is an electron going around it, and as it goes around, it emits radiation in a very particular direction and under very particular polarization. So synchrotron emission should be strongly polarized. We actually expect it to be like 70% or more polarized. So this opens up a question: why don't we see so much polarization? Now it seems like we see not enough polarization, and I will try to comment on that as well in the next slide or in a couple of slides. So another thing to consider, oh, by the way, the important thing is that this polarization vector works as K cross B, meaning wave vector times magnetic field, and the polarization should be orthogonal to both. So it's very important that the polarization pattern that we see should be orthogonal to the magnetic field. And this is how we can trace back the magnetic field. We look at the polarization pattern and we say that, oh, so magnetic field would be perpendicular to that. But another things are contributing. Well, for instance, all of that is propagating in a curved space-time. So we do need to consider this curvature when computing such things and when considering this orthogonality. It's locally orthogonal, but this propagation may make things more obscure for us to see. Nevertheless, you can make this very simple toy model kind of considerations. So imagine first that the magnetic field is toroidal. So magnetic field is being driven by the accretion flow and it loops around the black hole. There are loops of, the magnetic fields line are being dragged around the black hole in the accretion flow. So when you would expect that that polarization will be orthogonal to that. So if the magnetic field lines are going around the black hole, then you would expect the polarization to be radial like that. Then if your magnetic field is radial, on the other hand, the opposite things happen. The polarization would be azimuthal, perpendicular to that. Now for the vertical magnetic field, it turns out that this is the case where this geometry, this curved space-time geometry is the most important. And we do get something twisty like that. So this twistiness is actually probing the presence of the vertical magnetic field line components, which is kind of good because both Blandford-Payne and Blandford-Znajek mechanisms do require the vertical component of the magnetic field to be present to be able to energize the outflow. So this is a very nice professional animation that was made for us for like $6,000, I think, by the professionals. So imagine this is the magnetic field. So the toroidal situation or azimuthal situation is being driven by, dragged by the accretion flow. It means it's weak because it allows to be dragged by the material. If the magnetic field was strong, it would tell the gas where to go, not being dragged by the gas. And when we get this radial component that I've been talking about at the previous slide, now the strong magnetic field. This is strong, meaning it does not allow to be dragged by the gas. Gas is going around the black hole, but the magnetic field is of radial structure, and actually in this innermost part, it's magnetic field telling the gas what to do. So it means that gas does not necessarily just simply revolve around the black hole. Then somewhere in between, there is this situation where it's kind of strong. So just strong enough to not be totally azimuthal, not to be dragged around the black hole, but also not strong enough to just tell the accretion disk totally what to do. And it turns out that this looks like the situation we are looking at. These are the images of the EHT with the linear polarization, and they kind of resemble this pattern that you would expect. Sorry. Okay. Good. So these were very simple considerations just based on topology of magnetic field, but we can do, of course, more. And by doing more, I mean we can take 72,000 snapshots from different GRMHD simulations that make different assumptions about the underlying flow. We can look at what polarization they give us, and we can compare it with the data, with these different data parameters that I've been talking about. And it turns out that it's very discriminant, meaning out of those 72,000 snapshots, only of order of 100 is able to fulfill the requirements of the data. So really polarization, unlike total intensity, polarization is really killing a lot of GRMHD models. It really is constraining. It has a big constraining power. Oh, they even move. So I will give you quickly a couple of examples, what is good and matching the data well, and what is bad. So these are some snapshots from simulation that seem to be consistent with the data, sufficiently consistent. And at the bottom, these are some snapshots that are not consistent with the data. So in particular, you can see that we can get easily those radial patterns, which have nothing to do with what we see in the data, which also means that the magnetic field is, well, probably not purely azimuthal. And here you get too much polarization, here you get not enough polarization. There are different ways to discriminate some GRMHD snapshots. Now I told you that we have this little bit of problem that synchrotron radiation perhaps should be more polarized. Well, it turns out the answer is most likely the intrinsic Faraday rotation. So you know that as the radiation propagates through some matter, then there is this effect of Faraday rotation, meaning depending on the magnetic field presence, depending on the density of this gas, your EVPA, your polarization orientation is rotating. So usually this is not a huge problem for the astronomy, because what we usually assume is that there is a source and then there is a screen in which everything rotates the same. However, if you have intrinsic Faraday rotation, meaning different parts of your source experience different path through the matter, then Faraday rotation starts to scramble things around, because one part or one location in this image is experiencing different Faraday rotation than the other. So on average, there is different rotation, so those vectors do not add coherently. They can destroy one another. So this is the decoherence and depolarization through the intrinsic Faraday rotation. And this is the example of how it works. Without Faraday rotation, you can see this guy gets a lot of polarization. And without Faraday rotation, it's being depolarized quite strongly, meaning going from red to bluish color. So we expect that this is the reason why we see rather weak polarization, while the synchrotron emission should be in principle stronger. So what models of GRMHD survive our very restrictive matching with the polarized result? It turns out that it kills most of the sane models and prefers MED models. MED models are the models where magnetic field is strong. This is an acronym for magnetically arrested disk. Sane models are the ones where magnetic fields is not dynamically important. So it really shows us that the magnetic field is most likely dynamically important. And if you went that far with interpreting your results through the GRMHD simulations, you can also constrain more parameters like the accretion rate at M87. So we published before the total intensity limits on the accretion rate, but you see how wide they were. We couldn't really tell if this black hole is eating 1/10 of solar mass per year, or is it just eating 1 in 10,000 solar mass per year? So now with the polarimetry, we actually constrain it much better, and we see that this accretion rate is about, well, 1 sun per 1,000 year. So it's a very low accretion rate, actually. It is low luminosity AGN, this object that we are looking at. Okay, I'm almost done. I'm sorry for taking longer. I have like 2 more slides about future perspectives. So you see 2017, that was when these data were taken. That's the array we had observing M87 in 2017. We are actually done with 2021 observations with an expanded array. They finished like a week or 2 weeks ago. Unfortunately, we lost station number 4, station in Mexico, which is kind of central and important. But we do have Greenland now, which is also important. It gives us a lot of those baselines in the direction, in the north-south direction. So who knows, maybe this 2021 will be actually more interesting information about M87. And what could we use that for? Well, one big problem, probably the largest problem we have, like what is the thing we could wish for, is that we lack the dynamic range, which means that if we see the bright ring, then we don't see all this emission or all this outflow around it because it's too weak relatively to this bright crescent. So we don't have information about actually how the jet around it is forming. We only see this crescent. But it turns out that this dynamic range is mostly a function of a number of baselines, number of good coverage in the Fourier plane. And it turns out that we could actually, with adding just few more stations, we could see both the ring and this outflow. So really, that's only then we will really be studying the connection between this innermost part of the flow and outflow. So we're really looking forward to it. The picture I'm showing is, if these were the simulated data, that's what we would get in 2017. So we don't get this outflow properly, but this is NGHT, which is a concept of expanding the DHT by like 5 to 10 more dishes. So then we would really see this shape of the outflow pretty much consistently with the ground truth with the simulation. Okay, that is my last slide. It's a summary with some bullet points about what's interesting about these results. Let me just maybe highlight one thing, and I'm done after that, I promise. We find magnetic field of 1 to 30 Gauss. 1 to 30 Gauss is not a lot. 1 to 30 Gauss is, and we say it's strong. The Earth magnetic field is like half a Gauss. When you go into the MRI machine, it's like 10,000 Gauss. So this 1 to 30 is not huge. So why do we say that the magnetic field is strong and it's dynamically important? So of course it turns out it's large, but it depends with what you compare it with. So the density of gas is very low around M87. You just saw this mass accretion rate estimation. It's really not accreting much, meaning this magnetic field is strong, but with respect to other sources, with respect to other forces acting in this system. So it is dynamically strong, but it's not really like impressive from our point of view. It's nothing like the magnetic field of the magnetar. Okay, and now I'm done. Thank you very much. Sorry for taking like a full hour, I think. And I'm happy to answer your questions.
Thank you, Maciek, for a very nice talk. So do we have any questions? You can ask directly. It's not that many of us here.
I cannot see chat. I cannot see anything. Please just unmute yourself. And
yeah. So maybe I will start with my question. So the algorithm you use to produce the polarized pictures are you develop them as a EHT collaboration, or are they used in another observation?
Yeah, they have different stories behind them. So EHT imaging is something that is developed for the EHT, but we use it for years now. Even before getting first images, that was being developed and extensively tested on different data sets. This is the regularized max likelihood based method. PolSolve and LPCal are technically new methods, but they are not really developed for the EHT. They are relatively new. They are all based on this old idea of the clean algorithm, which is solving the problem as with putting a bunch of point sources. So now it's putting a bunch of polarized point sources and trying to kind of reverse engineer the distribution of brightness. So these are, in a spirit, these are very classic algorithms, because this clean is something that people do since 1970s. And this is like the most work in VLBI was done with algorithms based on these assumptions. Then DMC and FEMIS are also, they are custom made, but these are just the methods of exploring the posterior distribution. So these are statistical modeling MCMC based methods. Yeah, so it seems like, yeah, most of them are new, but it's just, you know, the reason is that we have kind of special needs. So we don't need special algorithms, but yeah, they make different choices. And I think apart from TEMIS, they are all publicly available also.
Okay. And so is the process of the processing of the data is now faster? So do you think that the data from this year publication, for example, will be available sooner than it took?
Yeah, I mean, that would be reasonable, wouldn't it? That would be a reasonable assumption. However, it's difficult to say. For sure, we learned a lot, and it should be faster. But will it actually be faster? We are also drowning in the old data at this point. Yeah, so I don't know. It should be faster, but I wouldn't be super optimistic about being much faster. Also, another interesting comment to make, I think, is that look, we now published total intensity. Then 2 years later, we published linear polarization. There is still circular polarization, which is the most difficult thing to get to squeeze out from the data. This is kind of, I don't even know if we will actually be able to squeeze out anything more. Will we be able to say something meaningful about the circular polarization? So we're really not even done with this first data set of M87 at this point.
And what can the circular polarization set? I mean, it can narrow the models, or
yeah, actually, circular polarization has some possibility to be even the most cost-constraining one. The problem is that it's also the weakest one we expect. We kind of expect the ordering that if total intensity is 1, when the linear polarization is 10%, when the circular polarization is 1%. This is, you know, kind of hand wavy order of magnitude ordering of those things. So really, it's difficult to get to something that is 1% because we have systematic errors that are of similar order. So we have to get them in order to be able to talk about circular polarization. But yes, in principle, circular polarization has a possibility to be perhaps even the most constraining. So it is tempting to invest some time into trying to get it. But again, I cannot say if we will be able to do that. We are working on that.
Thank you. Are there any other questions? Seems like they're not. Okay.
Well,
so
I'll stop sharing.
Thank you, Maciek, very much. It was nice to hear you again. And I hope next seminar will be announced soon.
Okay, great. Thanks a lot for listening. And well, you can also email me with questions. Most of you know my email probably.
Or can ask.
All right.
Okay, thank you very much. Maciek, can you wait a little bit longer? I would like to ask something.
Oh, sure, yeah.
Great, thank you.
Thank you, Maciek, for really nice talk. And take care.
Oh yes, take care.
And stay healthy.
Yes, and I hope to meet you soon in person.